Think about the sheer volume of data moving into and out of a computer at any given second. Every keystroke, every frame of video, every file transfer relies on a physical pathway to dock with the main system. Look closely, and every PC is essentially a massive assembly of standardized interfaces. Managing that system requires knowing these connections by sight. We break the ecosystem down into a simple taxonomy. On one side, internal components housed inside the case, CPU, memory modules, and storage drives. On the other, user-handled peripherals, monitors, keyboards, and external drives that interact with the environment. The point where these two worlds meet is the rear I/O panel. This is the physical junction point, packed with a diverse variety of interface shapes. To understand how these pathways function, we have to start with a precise distinction in terminology. A port is the hardware's static external connection to its internal bus interface. It is physically anchored to the device. A connector is the physical termination at the end of a peripheral's cable. It is the part designed to fit securely into a matching port. This distinction dictates how hardware is managed. Troubleshooting a connection requires identifying the specific communication protocol and maximum bus speed assigned to that physical interface. Let's look at the data domain. For decades, peripheral connections were highly fragmented until the Universal Serial Bus, or USB, standardized the pipeline. This chart tracks the exponential growth in USB bandwidth over time. We start in 1996 with USB 1.0, transferring at up to 12 megabits per second, and scale rapidly to 2019, where modern USB 4 hits up to 40 gigabits per second. Early USB architecture relied on strict logical separation. Data flowed outward from a host controller to a peripheral device, and the cable ends were keyed differently to prevent physical loops. You can see this separation in the hardware. The classic rectangular Type A connector is strictly for the host side. The square Type B connector is designed for receiving data on larger peripheral devices, like printers or scanners. As mobile devices shrank, the connectors followed suit. The industry introduced flatter, more compact form factors, first the Mini series, and later the Micro B layout, which became standard for older smartphones and tablets. Ultimately, this physical variety was streamlined into USB-C. Introduced alongside the 10 gigabit speeds of USB 3.1, the Type-C connector is reversible and capable of handling data, video, and power simultaneously over a single cable. That power capability introduces physical constraints. Delivering up to 240 watts through USB power delivery requires thicker gauge copper conductors to handle the load without overheating. That is why high-power charging cables are noticeably heavier. The arc of USB development is a direct move from dozens of highly specific plugs into a single, unified, high-bandwidth architecture. A similar demand for bandwidth drives the video domain, forced by rapidly increasing pixel counts and faster refresh rates. The exact data requirements depend heavily on the physical makeup of the display panel, whether it relies on OLED, LCD, or micro-LED technology. This macro photography comparison reveals the different subpixel arrangements. OLED uses individual organic compounds that emit their own light. LCD filters a continuous backlight through twisting crystals, and micro-LED utilizes microscopic inorganic diodes. Even within LCDs, the crystal alignment dictates performance. IPS panels align crystals parallel to the screen for high color accuracy, while TN panels twist them 90 degrees for faster response times at the cost of viewing angles. VA panels vertically tilt them on voltage for high contrast. Feeding millions of these subpixels 60 to over 100 times a second requires dedicated high-throughput physical ports. For modern displays, the primary interfaces are HDMI and DisplayPort. You can quickly distinguish them by their physical keying. HDMI has a symmetrical, tapered bottom, whereas DisplayPort features a distinct asymmetrical silhouette with a single flat corner. We also see the integration of Thunderbolt 3. This standard unifies high-resolution video and data transport, mapping directly onto the physical USB-C form factor. A display's maximum resolution and color depth are strictly bottlenecked by the bandwidth capacity of the specific interface connecting it to the graphics processor. Moving inside the chassis, we encounter the dedicated interfaces that govern internal storage drives and power distribution. For bulk storage, the serial ATA or SATA standard is used to connect fixed hard drives and solid-state drives to the motherboard. These connectors share a distinctive L-shaped physical key to prevent backward insertion. However, the short SATA data connector handles communication, while the wider SATA power connector draws current directly from the power supply. That brings us to the interfaces extending from the power supply unit itself. Older systems and certain specific peripherals still rely on legacy power standards, specifically the Molex and Berg connectors. The 4-pin Molex is a bulky connector historically used to power older IDE hard drives, optical drives, and case fans. Next to it is the smaller 4-pin Berg connector. This was designed almost exclusively for floppy disk drives, making it rare in contemporary systems. Internal hardware installation succeeds or fails on exactly matching the correct data and power pins to their precise counterparts on the board. On this motherboard, we can identify every interface. We see legacy DVI and VGA ports alongside modern HDMI and DisplayPort. Moving right, black USB ports indicate 2.0 speeds, while blue denotes 3.0. Finally, the Ethernet port sits above the analog audio jacks. When an IT professional looks at a computer case, they aren't looking at random plugs. They see a mapped system of standard bus-connected hardware interfaces. Recognizing the shape, purpose, and capability of these physical ports is the mandatory first step before attempting any upgrade, repair, or network installation. Every peripheral on a desk and every adapter card inside a chassis is locked into this ecosystem. Mastering the visual language of cables and connectors is the practical entry point to understanding how data actually moves through a system.